Okay. Next is that a further reduction in current carrying capacity occurs due to dielectric losses. If there is dielectric loss, means there is this thing, it will also help to increase the temperature. So, this factor limits the length of cables used in actual practice. So, that means you have to consider all the your what you call factors for this different type of losses you have to consider for the cables, right. So, next is over voltage due to switching. The interruption of capacitance currents give rise to the over voltage. Now, Ferranti effect you know. So, if a significant portion of the transmission and transmission line also you have seen that under no load condition the receiving end voltage is your what you call higher than the sending end voltage. Same is applicable for the cable also, right. Therefore, thus the voltage at the load point may vary considerably from full load to no load. So, in this case it may be necessary to use shunt inductive reactors in the system to avoid increase in voltage due to Ferranti effect. I mean, if the voltage rise, suppose in general, suppose if voltage rises within the permissible limit, say 1.05 per unit, say. So, if it is within the limit, say no question of the putting your what you call shunt inductive reactors. Otherwise, you have to put the your what you call in shunt inductive reactors, such that it will your what you call it will compensate the reactive power you are injected by the your shunt charging shunt capacitor, right. So, that is why shunt inductor is required such that it will compensate each other. That is why this Ferranti effect. I mean, in power system analysis course, in brief I have just told you that what is Ferranti effect. So, these are the things you have to consider. Next is some brief outline regarding HVDC cables, right. Now, when cables are used in direct current transmission, the main operational features are, I mean, for HVDC cable, high voltage DC cable, there is no charging current because this is a DC, only I square R losses are present. The electric stress distribution in AC cables is governed by dielectric capacitance. In DC cables, the stress distribution is determined by resistance of dielectric, right. This is the your what you call comparison between AC and DC cables, but the resistance of dielectric decreases appreciably with increase in temperature. Very interesting here, the resistance dielectric decreases appreciably with increase in temperature. The resistance of dielectric at 60 degrees Celsius may be about 1% of the resistance at 20 degrees Celsius, I mean drastic reduction, right. Therefore, the thermal consideration influence the electric stress distribution in the dielectric considerably, right. So, this is very interesting. Now, so in AC cables, the electric stress in the dielectric decreases from conductor to sheath, that we have seen near the surface of the conductor, that electric stress is higher, right, and when you are moving towards the your sheath, it is less. In DC cables, the electric stress increases and can be large at the sheath, just opposite. This phenomenon known as stress inversion, right, may lead to your troubles at terminals and joints where longitudinal traces are created. For HVDC cable, we will not study in detail, because we have to call your concept, we have to compensate this condense this cable part. Just some brief idea regarding HVDC cable, and because of the above features, DC cables can have very high current and voltage rating, right. So, because of this thing only, so these cables have lesser insulation thickness and are more compact. So, DC cables are always single core and conductor is always stranded, and it is suitable for high voltage. So, and its and cable may be plastic or impregnated paper insulation. Oil filled, gas filled DC cables are also used, right. So, cables having length more than 100 kilometer have been used in many places. So, this is the for compared to AC cable, HVDC you can use at high voltage level, right. And then your what you call many places up to 100 kilometer length cable have been used, but you have to consider all these things. But one thing is there, that cable is expensive than the overhead conductor. So, this cost is the main factor till date, otherwise the general idea of laying cable means that as you know that even it during storm or heavy rain or shower, that for overhead conductor there is a possibility of a fault, right, and where there will be the power supply disrupted, whereas in the case of cable that those things will not be there. But one thing is there, that cable is expensive than your what to call that your this thing an overhead conductor. But what we have learned, that some ideas regarding your what you call this cables, and your something we have seen that different type of cables, and your current rating and dielectric loss and all other things. So, with that cable will be topic is closed now, and next we will come to the transient over voltage and insulation coordination. So, this is a new topic, that your transient over voltages and insulation coordination. Let us see first what exactly it is. So, a transient phenomena is an aperiodic your function of time and has a short duration. You know that any transient phenomena is a aperiodic function of time and very short duration. So, example for such transient phenomena are voltage and current surges. So, we will start this thing I mean we will see step by step in a very simple manner. So, a voltage surge is introduced by sudden change in voltage at a point in a power system. If there is a sudden change in voltage, so that is what called the voltage surge will be introduced, and along with this a current surge will be always associated with that. So, for a common phenomena of this kind of thing is a lightning stroke, say, right. We will come to that those things later, right. So, its velocity depends on the medium in which the surge is travelling. So, such voltage surge always has an associated current surge with which it travels, right. If there is a voltage surge, then there will be associated current surge, along with it will travel, right. So, current surges are made up of charging or discharging capacitive currents that are introduced by the change in voltage across the shunt capacitance of the transmission line, that is your charging capacitance, right. So, that is why the current surges are made up of your what you call charging or discharging capacitive currents that are introduced by the your change in voltages across the shunt capacitance of the transmission system. Now, next is the surge voltage can be caused by lightning, switching or fault etc. Lightning stroke we will explain those things later on, that is you have seen again and again, and switching or faults etc. So, high voltage surges on power system can be very destructive to system equipment, because it will destroy everything, right. It can destroy transformer, even if sometimes your lightning arrestor also, right. When it travels from suppose some lightning stroke is there on the tower or on the shielded wire, that we will see later, that in both sides that travelling wave travels, right. So, lot of protections you have to take care for this very short duration, very short duration, that voltage surge. Thus, they must be limited to safe levels. While lightning strike a phase conductor or shield wire over a ground wire, right. If you look any tower, you will see that one ground wire will be there at the top of the tower, right. So, the current of the lightning stroke tends to divide half going in each direction. I mean, when lightning stroke happens, that wave actually moves both sides half, right. If the overhead ground wire is struck at the tower, right, current will also flow in the tower, including its footings and counterpoise. I mean, you have to take care of this your what you call from this lightning stroke, because lightning stroke is a very common phenomena, right. So, now the current of the lightning stroke will see the surge impedance of the conductor or conductors. If it is a if you have your what you call that many more than one conductors in any phase, or the 3 phases single conductor, 3 conductors are also there, right. So, that a voltage will be built up, right. So, as stated before, both the voltage and the current will move along the conductor as travelling waves. So, if such strokes happen, then that both the voltage and the current will move along the conductor as a travelling wave. It is later we will see that it happens in microsecond, right. So, studies of transient disturbances in a transmission system have shown that lightning stroke and switching operations are followed by a travelling wave of a steep wave front, right. It will be unidirectional. So, when a voltage wave of this type reaches a power transformer, for example, it causes an unequal stress distribution along its windings and may lead to breakdown of the insulation system. Suppose very simple example is, suppose a transmission line, that lightning stroke happens on the top of the tower or conductor or the sealed wire, then lightning or what you call that wave travels to the nearby, if nearby substation is there, it will travel to that, and substation, you know, step up or step down transformers are there. So, if that in that case what will happen, this kind of wave that it reaches power transformer, say at the substation for example, it causes an unequal stress distribution along its windings and may lead to breakdown of the insulation system. So, that winding insulation, there will be breakdown and transformer will be damaged. So, lightning is a lightning stroke particularly is a very strong phenomena, and you have to protect the power system. So, I will come to this figure later on. Therefore, it is required that the insulation behavior be studied under such impulse voltages. That means, that is your what you call that whenever they go for, suppose manufacturer, when they manufacture transformers for example, say they go for laboratory test, that your impulse test, right, because it will last for microsecond, and whether that transformer insulation it can sustain or not, right. So, an impulse voltage is unidirectional voltage. This is actually unidirectional voltage that rises quickly to a maximum value and then decays slowly to 0. So, we will come to that. The wave shape is referred to as T1 into T2. They call it is T1 into T2, where both values are given in microsecond. For example, if you look at the graph, this side it is microsecond, right. It is and this side is a voltage per unit. Now, if this voltage reaches, it is 1 point, it is a microsecond. If T1 is equal to 1.2 microsecond, if it reaches its crest value, that is peak value, that is 1, right, and finally it is coming to that your this is wave front and this is wave tail, and if it reaches 50% of it at 50 microsecond, right. So, that is they call T1 into T2 as shown in figure 1. But let me tell you, this is a standard case, but in reality it does not happen. I have seen also that this kind of test, and you found it may not be sometimes 1 point your what you call 2 microsecond, it may be 1.3, it may be 1.4. Here also all the time it cannot be 50 your microsecond, it also changes, but this is a special case. So, this is your wave front as long as it is rising, and wave tail when it is decreasing, but time is very fast in microsecond range, right. So, the international, this is the international standard wave shape, international standard wave shape, right, that is they call T1 into T2, it is 1.2 into 50, this is the international standard, but in reality this may not happen, it may change this way or that way, right. So, note that crest value of the voltage is reached in 1.2 microsecond, this is 1.2 microsecond, right, and the 50% point on the tail of the wave, that is at 50 microsecond. I told you this one. Of course, not all of the voltage waves caused by lightning can conform to this specification. Even if you go for laboratory test for impulse voltage test, right, you will not find that your what you call 1.2 or 50, it may change, but this is standard. Now, the travelling wave, before telling you all sort of things, this is a voltage source is given, say, and suppose representation of 2 wire transmission line for application of travelling waves, and this is a lumping representation. What you do, suppose you have a transmission line, resistance for the time being we have neglected, right. This is sending end and this is receiving end, and this capacitance C1, C2, C3, C4, C5, Cn minus 1 up to Cn, this is the charging capacitance, right, line to ground, and this inductance also lines are divided into infinitesimal small sections. So, L1, L2, L3, Ln, it is like this. Now, suppose this there is a voltage, right, voltage source, and there is a switch. Now, what will happen? As soon as you know from the circuit theory, as soon as you close the switch, this capacitance will be charged, right. So, this capacitance will be charged, but at the same time, at the time of switching, we are imaging, we are your what you call we imagine that these are in infinite smaller your what you call section. So, but this inductor as soon as you switch on, you know how the inductor will behave. Inductor will be open circuit, right. So, if inductor is open circuit means the immediately the voltage across C2 will not be developed, it will take some time. Similarly, when C2 voltage will develop, then C3, then it will come. That means a wave will travel from sending end to receiving end this way. I repeat that suppose you have a voltage source, there is a switch, and these are all the charging capacitance. Each line section it is taken infinite your decimal small length. So, inductance is given L1, L2, L3, Ln, right. Now, question is, as soon as you close the switch, this capacitor will be charged immediately, because you know from the circuit theory that as soon as you switch on, that capacitor will behave like a short circuit and inductor will remain open circuit. It will be charged, but it will remain open, it will be open circuit, it will act like open circuit, neglecting the resistance of the line, say. So, similarly, voltage immediately voltage will not be built up here, you cannot get voltage immediately across this, because it will act as open circuit, right. So, it will take some time. Similarly, when voltage you will get the voltage across this will remain open. So, what will happen, this way it will move as if a wave is travelling from the sending end to the receiving end. So, this is the philosophy. Now I have given the description. Now, to study transient problems on a transmission line in terms of travelling waves, the line can be represented as incremental section. This is all incremental section we have taken in figure 2a, right. And so, it is lumpy representation, we calling that this is figure 2 and this is your what you call A. So, B will come later, right. So, this case the 2 wire line is shown with one phase and neutral return, is one phase and neutral return, right. The parameters L and C, you know, inductance and capacitance of the line respectively. So, to simplify the analysis, what we have done, resistance and conductance G we have assumed 0, that is they are neglected, you just for the purpose of explanation. So, any disturbance on the line can be represented by the closing or opening of the switches as shown in figure 2a. So, this is the switches, and any disturbance is switch your what you call closing or opening will create a disturbance in the line, right. For example, when a line is suddenly connected to a voltage source, the whole of the line is not energized instantaneously. I told you, if you close it, whole of the line cannot be charged instantaneously. In other words, if the voltage V is applied to the sending end of the line by closing switches, that means this voltage is applied by closing V, by closing the switches, right. The voltage does not appear instantaneously at the receiving end. I told you immediately it will not be appear, it will travel, the phenomena I have told you, right. So, that means just hold on. So, when switch S is closed, I told you all these things, now written something for you, that when switch S is closed, the first capacitors become charged immediately to the instantaneous applied voltage. I told you immediately, because capacitor acts as a short circuit and inductor will act as open circuit, right. So, however, because of the first series inductor, since it acts as an open circuit, the second capacitor does not respond immediately, but is delayed, right. This phenomena will happen from the sending end to receiving end, right. Similarly, the third capacitor, this one is delayed still more by the existence of the second inductor, and so on. Therefore, the farther away from the sending end to the line, the greater is the delay. This gradual build up of voltage over the transmission line conductors can be regarded as though a voltage wave is travelling from one end to other end. I mean, if this phenomena continues, then from the sending end to receiving end, I told you as if a voltage wave is moving, right. And the gradual charging of the voltage capacitance is due to associated current wave. That means, this any voltage wave I told you will be associated with current wave. So, due to this associated current wave, this all the capacitance will be charged and so on, right. So, just hold on, and if the applied voltage is on the form of a surge, suppose if the applied voltage is in the form of a surge, say, then starting from 0 and returning again to 0, suppose it is just a your what you call, it is form of a surge, starting from 0 and returning again to 0, therefore, it can be seen that the voltage on the intermediate capacitor rise to some maximum value and again return to 0, right. So, disturbance applied the disturbance of the applied charge is therefore propagated along the line in the form of a wave, right. So, this kind of disturbance we will be see therefore propagated in the form of a wave. I mean every voltage wave, a current wave will be associated with it, right. Such a propagation of the sending end voltage and current conditions along the line is called travelling waves. So, that is why its name is travelling wave, right. Your sending end voltage and current along along the line is called the travelling waves. Therefore, the voltage and current functions of both x and t, we can represent it, that is, it is V is equal to V function of x and t. I will show you what, and I is equal to I x in t. I mean, if this is the direction, this is the later I will show you. This is the direction is x and moving along time. So, V is a function of your x and t, and I also is a function of x and t, right. That means this the series voltage drop along the your what you call elemented length of line, that small line can be expressed as, I mean, now what you do, you consider a small section of line, this side current is I, this and distance is measured from, I mean, from sending end to the receiving end, I mean distance is increasing from sending end to receiving end, this way we have taken, and voltage here is V, right, polarity is shown, and as it is a small elemental section. So, inductance you say delta L, right. I mean delta L means if total inductance is L, say total inductance is L and length is say dx, delta x rather, delta x, then delta L actually is equal to L into delta x, right. So, this is your delta L. That means, this L we are representing say Henry per meter, say milli Henry or Henry whatsoever, right. So, this is actually delta L, same is applicable for capacitor. Now, when here say this is a small section, of course, if this is say sending end side, or I will say this is input side, output side, the current will be I plus del I upon del x into dx. This is actually almost same type of representation like your long transmission line, that analysis whatever you have studied, right. And voltage here will be V plus delta V upon delta x into dx. So, this portion, this elemental length is delta x and distance is increasing from your left to right, the distance is increasing. This is element section of line, right. Therefore, delta V, this in bracket I am writing function of x and time. So, delta x comma t is equal to this side voltage, you can write here, it is not shown in a function of V in x t again and again, but it is understandable. I means I function of I x t, V means V function of also x t. So, delta V delta x comma t is equal to V in bracket x t minus V this side when it is coming x plus delta x, here it is x plus delta x. So, minus V x plus delta x comma t. So, this one one can write delta V delta x t integrate x to x plus delta x L into del I del t into this thing. I just told you actually it is your in general just if when you write no V is equal to L into d I by dt you write. So, if it is a small voltage delta V is equal to delta L into d I by dt, that you write. So, delta L is equal to L into dx, that is L into d I by dt into delta x. So, here we are taking partial derivative, right. So, that is why this equation we are writing L into dx means that is delta L, right. So, it is L del I dt dx. So, this equation actually or in the limit as x delta x approaches to 0, this limit you can write here I am writing in a function of t, but you can directly write del v of del x, it is understandable, del v x t del x is equal to minus L your del I x t dt. Why this minus sign is coming, I will come to that later, right. So, that means del v of del v now I am not writing again and again. So, del v del x is equal to minus L del I your dt, that is equation 3, right. So, here minus sign will, because x is increasing, you can write here also, if you take minus common, it will be v x plus delta x comma t minus your v x t. Anyway, we will come to that later. Similarly, the current to change the infinitesimal capacitance can be expressed as we know that your what you call del I del x, I writing I is a function minus c into your del v dt, v is a function of x t, right. So, this equation we can write like this, I mean from this figure, from this one, right. So, we can write that del I del x is equal to minus c del I x to dt. Just once I have written, after that again and again I am not writing I is a function of x t or v is a function of x t, but it is understandable. That means del I del x is equal to minus c into dv by dt. Actually, your this same as before, right. If you take delta c also, it will be c into your delta x, right. So, that is why you can write del I del x is equal to minus c into dv by dt, equation 5, this one, same philosophy. Now, note that negative sign in equation 2 and 5, this is equation 2 and this is equation 5, right, are due to the direction of progress at distance x along the line. As it is moving from left to right, it is increasing. So, if you try to make it like this, that delta v x t, we are writing v x t minus this thing, you take minus common, it will be v x plus delta x t minus v x t, automatically it will come to this. So, it is your x is increasing from left to right, right. So, figure 2b shows that this figure, this is the figure, it is 2b, this figure, it shows that x is increasing to right. Therefore, based on the given current direction, both voltage V and current I will decrease with increasing x. That means, as x is increasing both left to right, therefore, the both voltage V and current I will decrease with increasing the value of the x, right. Now, so I can be eliminated from equation 3 and 5 by taking the partial derivative of equation 3, that means this equation with respect to x and equation 5 with respect to t. Now, equation 3 is this one, equation 3 is this one, right. Equation, you come back to equation 3, that is this one, you take the derivative this one with respect to x. So, this will become del square v del x square, that is del square v del x square is equal to minus L, it is L into del I del x del t minus L into del I del x del square I del x del t. This is equation 6. Similarly, this equation 5, if you take derivative with respect to t, this equation 5 with respect to t, then it will be your del square I del x del t is equal to minus c del square v del t square. This is equation 7. So, that means equation 3 you take derivative with respect to x and equation 5 you take derivative with respect to t, right. Therefore, if you after getting these two equations, you substituting equation 7 into equation 6, that means if you substitute this one equation your 7, that is del square I del x del t is equal to minus c del square v dt square, here you substitute this one here. So, minus minus plus, so it will be L c del square v del x square is equal to L c, it will become your del square v dt square. This is equation 8. Okay, we will come back again.